ground fault on a heat tracing wire leading to a high voltage circuit trip can be perplexing, but there are several potential explanations. Firstly, ground fault propagation. The initial ground fault on the heat tracing wire may have caused a voltage rise on the neutral point of the 480 volt system. This voltage rise could have propagated to the high voltage side of the transformer via capacitive coupling or other mechanisms triggering the high voltage earth fault protection. Secondly, harmonic distortion. The high short circuit current during the initial ground fault may have generated harmonics in the system. These harmonics could have caused resonance with the transformer or other components, leading to overvoltages and insulation breakdown in the high voltage circuit. Thirdly, equipment failure. The transformer itself or the high voltage earth fault relay may have malfunctioned, triggering a false trip even in the absence of a high voltage ground fault. A faulty connection or grounding issue in the relay could also be a contributing factor. Fourthly, Arctic conditions. Extreme cold and moisture in Arctic conditions can affect the insulation and conductivity of electrical components. These conditions may have weakened the insulation between the high voltage and low voltage circuits, contributing to the failure. Fifthly, grounding system issues. The grounding system, including the copper plate in seawater, may not be providing adequate protection against ground faults. Corrosion or other issues in the grounding system could have reduced its effectiveness, leading to the propagation of the fault to the high voltage circuit. To investigate this issue further, consider these actions. Firstly, thoroughly inspect the grounding system, including the copper plate in all connections. Look for any signs of corrosion or damage that could compromise its effectiveness. Verify that the grounding connections are tight and properly made. Measure the ground resistance to ensure it meets the required standards. Secondly, check the transformer for any signs of damage or overheating. Inspect the transformer windings for any signs of insulation breakdown or damage. Check the oil level and condition, if applicable. Perform an insulation resistance test on the transformer windings. Thirdly, calibrate and test the high voltage earth fault relay to ensure proper operation. Verify that the relay is set to the correct settings for the system. Perform a functional test of the relay to ensure it trips properly when a ground fault is detected. Inspect the relay connections for any signs of corrosion or loose connections. Fourthly, analyze the harmonic distortion levels in the system and mitigate any potential resonances. Use a harmonic analyzer to measure the harmonic distortion levels in the system. Identify any potential sources of harmonics, such as variable frequency drives or nonlinear loads. Install harmonic filters to reduce the harmonic distortion levels. Fifthly, consider using surge arresters or other protective devices to safeguard the high voltage circuit from transient overvoltages. Surge arresters can help to protect the equipment from damage caused by lightning strikes or switching surges. Ensure that the surge arresters are properly sized and installed for the system. To elaborate on ground fault propagation, it's important to understand how a ground fault in a low voltage system can affect a high voltage system connected to a transformer. Transformers are designed to isolate the high voltage and low voltage circuits, but there are still mechanisms by which a ground fault can propagate. One mechanism is capacitive coupling. There is always some amount of capacitance between the windings of a transformer. During a ground fault, a voltage surge can occur on the low voltage side, and this surge can capacitively couple to the high voltage side. If the surge is large enough, it can exceed the insulation withstand voltage of the high voltage system and cause a flashover to ground, resulting in a high voltage trip. Another mechanism is through the grounding system itself. If the grounding system is not properly designed or maintained, it can provide a path for the ground fault current to flow back to the source through the high voltage system. This can happen if the ground impedance is too high or if there are multiple ground points in the system. Now let's delve into harmonic distortion. Harmonics are voltage or current waveforms that are multiples of the fundamental frequency of the power system, which is typically 60 Hz. These harmonics can be generated by nonlinear loads such as variable frequency drives, electronic ballasts, and computers. Harmonics can cause a variety of problems in electrical systems, including increased heating of equipment, voltage distortion, and equipment malfunction. In the case of a ground fault, the high short-circuit current can exacerbate the harmonic distortion in the system. These harmonics can then resonate with the transformer or other components, leading to overvoltages and insulation breakdown in the high-voltage circuit. Regarding equipment failure, it's crucial to consider the possibility that the transformer itself or the high-voltage earth-fault relay may have malfunctioned. Transformers are complex devices, and they can fail for a variety of reasons. Some common causes of transformer failure include insulation breakdown, winding damage, and core damage. The high-voltage earth-fault relay is designed to detect ground faults on the high-voltage side of the transformer and trip the circuit breaker to protect the equipment. However, relays can also malfunction due to faulty components, corrosion, or incorrect settings. The Arctic conditions can play a significant role in electrical failures. Extreme cold can make insulation brittle and more susceptible to cracking. Moisture can also penetrate insulation and reduce its dielectric strength. Corrosion is also a major concern in Arctic environments due to the presence of salt and other corrosive elements. As for grounding system issues, a properly designed and maintained grounding system is essential for protecting electrical equipment and personnel from ground faults. The grounding system should provide a low impedance path for the ground fault current to flow back to the source, which will cause the circuit breaker to trip and de-energize the faulted circuit. If the grounding system is not adequate, the ground fault current may flow through other paths, such as the high voltage system, which can cause a trip. The copper plate in seawater is intended to provide a low resistance ground connection. However, seawater is highly corrosive, and the copper plate can corrode over time, which will increase its resistance and reduce its effectiveness. In addition to the recommended actions, it may also be helpful to perform a power quality study to identify any potential problems with the electrical system. A power quality study can measure voltage and current harmonics, voltage sags and swells, and other power quality parameters. This information can be used to identify the root cause of the problem and develop a solution. In the context of the 480 volts and 4160 volts systems, it is important to understand the specific grounding configurations used. The 480 volt system, derived from a delta Y transformer, typically has a grounded Y secondary. This means that the neutral point of the Y winding is connected to ground, providing a reference point for voltage and a path for ground fault current. The 4160 volt system's grounding is equally critical. Depending on the utility and local regulations, it may be a solidly grounded, impedance grounded, or ungrounded system. Solidly grounded systems provide a low impedance path for ground fault currents, resulting in high fault currents and fast clearing times. Impedance grounded systems use a resistor or reactor to limit the ground fault current, reducing stress on equipment but potentially increasing fault clearing times. Ungrounded systems, while technically grounded through stray capacitances, allow for continued operation during a single ground fault, but can experience overvoltages during subsequent faults. When investigating the grounding system, several factors need to be considered. The size and material of the grounding conductors are important. Grounding conductors must be large enough to safely carry the maximum expected ground fault current. Copper is a common material for grounding conductors due to its low resistance and corrosion resistance. The connections in the grounding system must be tight and free of corrosion. Loose or corroded connections can increase the ground impedance and reduce the effectiveness of the grounding system. The ground resistance should be measured at various points in the system to ensure that it meets the required standards. A high ground resistance can indicate a problem with the grounding system. In addition to the grounding conductors and connections, the grounding electrodes are also important. Grounding electrodes are typically rods or plates that are buried in the earth and connected to the grounding system. The number and type of grounding electrodes required will depend on the size of the electrical system and the soil conditions. The soil resistivity is a measure of the resistance of the soil to the flow of electrical current. High soil resistivity can make it difficult to achieve a low ground resistance. In Arctic conditions, the soil can be frozen for much of the year, which can significantly increase the soil resistivity. The copper plate in seawater is used as a grounding electrode in this case. Seawater is a good conductor of electricity, so it can provide a low resistance ground connection. However, as mentioned earlier, seawater is also highly corrosive, so the copper plate must be inspected regularly for corrosion. The type of heat tracing system is also relevant. Heat tracing systems are used to prevent pipes and equipment from freezing in cold climates. There are two main types of heat tracing systems: self-regulating and constant wattage. Self-regulating heat tracing systems automatically adjust their heat output based on the temperature of the pipe. Constant wattage heat tracing systems produce a constant amount of heat, regardless of the pipe temperature. The type of heat tracing system can affect the magnitude of the ground fault current. Self-regulating heat tracing systems typically have lower ground fault currents than constant wattage heat tracing systems. When troubleshooting this issue, it's important to follow a systematic approach. Firstly, gather as much information as possible about the failure. This includes the date and time of the failure, the location of the failure, the type of equipment that failed, and any other relevant information. Secondly, visually inspect the equipment for any signs of damage. This includes looking for cracked insulation, loose connections, and signs of overheating. Thirdly, perform electrical tests on the equipment. This includes measuring the insulation resistance, the ground resistance, and the voltage and current levels. Fourthly, analyze the data to determine the root cause of the failure. This may involve using a power quality analyzer to measure harmonics and other power quality parameters. Fifthly, implement corrective actions to prevent future failures. This may involve replacing damaged equipment, improving the grounding system, or installing harmonic filters. Regarding the Westinghouse relay, it's important to verify its proper operation and settings. Relays are critical components of protection systems and must be calibrated and tested regularly. Firstly, check the relay settings to ensure they are appropriate for the specific application. The settings should be based on a coordination study to ensure that the relay will trip before other protective devices. Secondly, perform a functional test of the relay to ensure that it trips properly when a ground fault is detected. This test should be performed using a relay test set. Thirdly, inspect the relay connections for any signs of corrosion or loose connections. Loose connections can cause the relay to malfunction. When performing electrical tests, it's important to follow proper safety procedures. Always de-energize the equipment before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards of electricity and take steps to avoid them. Consider the age of the equipment involved. Older transformers and relays may be more susceptible to failure due to aging insulation and components. If the equipment is old, it may be time to consider replacing it. It's also worth noting that multiple factors may have contributed to this failure. It's not uncommon for electrical failures to be caused by a combination of factors rather than just one single cause. Therefore, it's important to consider all of the potential causes and take steps to address them all. Another aspect to consider is the potential for transient overvoltages. Transient overvoltages are short-duration voltage spikes that can occur due to lightning strikes, switching operations, or other disturbances. These overvoltages can damage electrical equipment, especially if the insulation is weak. Surge arresters can be used to protect equipment from transient overvoltages. Surge arresters are devices that divert the overvoltage current to ground, preventing it from damaging the equipment. It is also important to consider the potential for voltage imbalances. Voltage imbalances can occur due to imbalanced loads or faulty equipment. Voltage imbalances can cause equipment to overheat and fail. Voltage imbalances can be measured using a power quality analyzer. If voltage imbalances are present, they should be corrected. In addition to the technical aspects, it's also important to consider the human factors involved in this failure. Were the maintenance procedures adequate? Was the equipment properly installed and maintained? Were the operators properly trained? Addressing these human factors can help to prevent future failures. Consider consulting with a qualified electrical engineer or power quality expert to get a professional opinion on this issue. They can perform a detailed analysis of the system and recommend appropriate solutions. Finally, document all of your findings and actions. This will help to track the progress of the investigation and to prevent future failures. Good documentation is essential for effective maintenance and troubleshooting. Remember to prioritize safety when working with electrical equipment. Always follow proper safety procedures and use appropriate personal protective equipment. Electricity can be dangerous, so it's important to take precautions to avoid injury. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical engineer or other expert before making any decisions about electrical equipment. In summary, the high voltage trip following a low voltage ground fault is a complex issue with multiple potential causes. Thoroughly investigating the grounding system, transformer, relay, harmonics, and Arctic conditions is crucial. Implementing corrective actions based on the findings, along with a focus on safety and proper maintenance, will help prevent future occurrences.